Chapter 9 is all about chemical bonding. So we're going to revisit some concepts that we've already talked about, including ionic bonding and covalent bonding, and introduce a new type of bonding called metallic bonding. So the first thing we'll address is a Lewis electron dot symbol. A Lewis electron dot symbol is different than a Lewis dot structure for those of you who are already familiar with it, but it's something that we will use in the next chapter. And a Lewis electron dot symbol is the atomic symbol for an atom, which represents the nucleus and the inner electrons. And then we place dots around the symbol to represent all of the valence electrons. And so if you want to draw a Lewis electron dot symbol for any atom, first determine how many valence electrons you have, and then you're going to place one dot at a time on each of the four sides of the elemental symbol to represent the valence electrons. And if there are more than 4 electrons, then you start to pair the electrons until all of them are represented. And so for an element like carbon, this would be the electron dot symbol. There are 4 valence electrons because carbon is in group 4A, and we would put one dot on each side to represent those 4 valence electrons. If we have an element like chlorine, which has more than 4, it actually has 7 valence electrons, and you would know that because it's in group 7A, or you could write its electron configuration and know that the 7 valence electrons are in the 3rd energy level. So to draw the Lewis dot symbol, we would start by writing chlorine, Cl, and you can pick any one of the 4 sides to start on. I decided to start on the top and do 1, 2, 3, 4. Once we have 1 on each side, we begin pairing them. 5, 6, 7, and now all 7 of the valence electrons are represented on chlorine. Some of you may wonder, does it matter which side the single dot is on? And no, it does not. As long as 3 of the sides have a pair of electrons and 1 of the sides has an unpaired electron. And so here are the Lewis dot symbols for elements in periods 2 and 3, and just the main group elements. And so in group 1A, we have elements that have 1 valence electron, so there's 1 dot. In 2A, there's 2 valence electrons, so there's 2 dots. And you move all the way across until you get to the noble gases, which have 8 valence electrons, and there'll be a pair of electrons on each side. And so if you're asked to draw the Lewis dot symbol or identify the Lewis dot symbol for an element like nitrogen, any one of these 4 would be correct, where you have 5 valence electrons for nitrogen, meaning there's a pair on one side and 3 unpaired electrons on the other 3 sides. So any one of these 4 is appropriate. This one on the right here would represent an incorrect Lewis dot symbol because we have an empty side, so a side where there are no electrons, and 2 sides that are already paired up. So let's practice identifying the correct Lewis dot symbol for a given atom. If we have barium, the first thing you want to do is figure out how many valence electrons does barium have. So we find it on the periodic table, we identify that it is in group 2A, so we would expect barium to have 2 valence electrons. So you can immediately eliminate choices 3 and 4 because they don't have 2 valence electrons shown. And so we are choosing between choices number 1 and number 2. And the correct way to represent the Lewis dot symbol for 2 electrons would have them spaced out as far apart as possible. And since they're paired here, that is definitely incorrect. So we would choose choice number 2 for barium. For silicon, again, first figure out how many valence electrons does it have. So finding it might be the hardest part. Silicon is in group 4A, so it will have 4 valence electrons. We can immediately eliminate choice number 4. And so when we're deciding between these 3, we want the electrons to be spaced out as far as possible. And so choice number 3 would be the only correct way to represent those 4 electrons. There should be no empty sides. The final example, phosphorus. Phosphorus is in group 5A, so it will have 5 valence electrons shown. We have 3 choices that have 5 valence electrons, this one, and this one. And the one that correctly represents the distribution of those electrons around the atom would be choice number 1. That brings us into bond formation. Why do atoms even bother forming bonds? Why don't they just stay elements all by themselves? Well, remember, pretty much everything in chemistry is driven by energy. And when an atom bonds with another atom, via having the valence electrons interact with one another, it lowers the overall potential energy of each of the atoms. So energetically, it's favorable for all atoms involved. And so most of the atoms on the periodic table are going to follow what we call the octet rule. And so when they form bonds, they're either going to lose, gain, or share electrons in an attempt to attain a filled outer energy level of 8 electrons. So octet comes from the number 8. There are a couple of exceptions to that. There are some elements that are too small. They don't have enough energy levels or enough space for 8 electrons on its outermost energy level. And those exceptions include elements like hydrogen, helium, lithium, and beryllium. They're happy with just 2 electrons in their outermost energy level because their outermost energy level is energy level number 1. And remember, we can only fit 2 electrons in the first energy level because there's only an s sublevel available. But essentially all other atoms are going to follow the octet rule. There are a couple more exceptions to that, which we'll go more in depth in chapter 10 when we get to Lewis structures. And so as an example, you know that sodium and chlorine will often interact with one another, where sodium will donate 1 electron to chlorine to form an ionic bond between the 2 elements. And the reason that they do this is because when sodium gets rid of 1 electron, it's got 1 valence electron, it becomes the sodium ion, and now its outermost energy level, which is now energy level 2, has 8 electrons around it, thereby following the octet rule. Chlorine will happily take in that extra electron because the chlorine atom has only 7 valence electrons, and when it accepts that final electron, it's going to have 8 electrons on its outermost energy level, and it will follow the octet rule. We've already talked about ionic bonding and covalent bonding, and we're going to introduce another type of bonding called metallic bonding, which is between only metals. And so the bonds differ in the way the electrons interact with one another and the types of elements that are involved. And so generally, you already know that ionic bonding is between metals and nonmetals, and there is a transfer of electrons. The metal will donate its electrons to the nonmetal. And this is energetically favorable for all elements involved. We've also already talked about covalent bonding, where there's going to be sharing between electrons. Remember, nonmetals do not like to give their electrons away because they have a high ionization energy, but they do like to gain electrons. And so what they will do is they will share their electrons with other nonmetals. And so if you only have nonmetals, you would expect there to be covalent bonding. One type of bonding we haven't talked about yet is like, what if you only have metals present? How are those electrons going to interact with one another? Remember, metals will easily give away their electrons because of their low ionization energy, but they don't have a very strong electron affinity. Their electron affinity is quite low. And so the way that metals interact with one another is by forming what's called an electron sea. And so if you have a whole bunch of metals next to each other, it can be metals of the same type or different types of metals. Each of those elements is trying to get rid of an electron or multiple electrons in order to satisfy the octet rule. And so what it does is it will take its valence electrons and pass it to the next element. That element doesn't really want those electrons because it also is trying to satisfy the octet rule. And so it'll pass its electrons on to the next atom. And so you essentially have a quick game of hot potato where these electrons are shuffling between these metallic atoms to form what we call an electron sea. And so let's practice identifying the type of bonds based on just a chemical formula. And so essentially what you want to do is identify whether you have a mixture of metals and nonmetals, just metals or just nonmetals, and then identify the type of bond that would be present between those. If you have just the element chromium, so chromium is one of your transition metals, and you would expect chromium, just because there's only metals present, to have metallic bonding. For the next example, carbon dioxide, we have carbon and oxygen, and both of those are nonmetals, and so you would expect this to be a covalent bond. Those elements would be sharing electrons. Then we have calcium oxide. Calcium is a metal, oxygen is a nonmetal, and so if you have a metal and a nonmetal, you would expect there to be a transfer of electrons, which would represent ionic bonding. This complicated substance right here, I believe this is a triglyceride found in butter. You've got carbon, hydrogen, and oxygen only. All of those are nonmetals, so you would expect there to be covalent bonding between those elements. And the last example, bronze, which is an example of an alloy. An alloy is a mixture of metals, a homogeneous mixture of metals. Bronze specifically is copper and tin, and both copper and tin are metals, so you would expect there to be metallic bonding present between these two elements. We won't spend too much time on ionic bonding because we've already talked about ionic compounds quite a bit throughout this semester. but you know in general that an ionic bond occurs when you have a metal transferring one or more of its electrons to a nonmetal, and sometimes that anion can be a polyatomic ion. And as an example, using the electron configurations and orbital diagrams for elements like lithium and fluorine, when lithium fluoride is formed, it does so because lithium has one valence electron, and if it donates that one electron, it becomes the lithium ion, and its outermost energy level 1, is completely filled with electrons, satisfying its quote-unquote octet rule. And fluorine has one vacancy in its outermost energy level, the fluorine atom, and so it's going to accept that one electron. And now when it does that to form the fluoride ion, it has an outermost energy level 2, completely filled with electrons, satisfying the octet rule for fluorine. There are some important properties about ionic compounds that you should generally be familiar with. Certainly there are some deviations from these properties, but it's something that is common between many ionic compounds. And if you think of sodium chloride, or if you think of table salt, that sort of exemplifies the properties of ionic compounds. Most of them are going to be solids at room temperature. They tend to be hard, rigid, and brittle. The electrical conductivity is an important property of ionic compounds. In the solid state, so if you have the solid ionic compound, it's not going to conduct electricity at all. However, if you melt the solid, so you heat it to a melting point so that it becomes a liquid, that substance will conduct electricity. But you'll notice that the melting points for ionic compounds tends to be really high, so you would have to maintain it at that high temperature in order to get that conductivity. And also, if you take the ionic compound and it is soluble in water, when you dissolve it in water, it will conduct electricity. And we talked about that in chapter 4 with the concept of electrolytes. And so remember, ionic compounds, when dissolved in water, represent strong electrolytes. They conduct electricity very well. And the melting points are very high for ionic compounds. You can see down here, these are all melting points of these substances that are represented. And as a result, their boiling points are also very high. Next, we'll talk about covalent bonding. We're going to focus a little more on covalent bonding in this chapter. And then we'll move on to Lewis structures in chapter 10, which is entirely covalent bonding. And so if you think about the different combinations of metals and nonmetals that you can put together for ionic compounds, you're actually quite limited in the number of combinations that you have. But if you were to think of all the possible combinations of nonmetals that you could put together, you're not limited by the ratios of them. So essentially you have an infinite combination of nonmetals that you can have to make different molecules. And just to give you one extreme example of a molecule, the molecule insulin, which everyone has in their body, which helps regulate your blood sugar, one molecule of insulin has 257 carbon atoms, 383 hydrogen atoms, 65 nitrogens, 77 oxygens, and 6 sulfur. That's one insulin molecule. So covalent bonds result when you have 2 or more nonmetals sharing electrons. And so this is clearly more than 2 nonmetals. All of these elements are combined in such a way that they're sharing their valence electrons to form covalent bonds. So why do the elements share electrons? Remember, it's all about potential energy. When the elements are sharing electrons, it lowers the overall potential energy of those elements. And to use hydrogen as an example, remember, hydrogen is one of your diatomic elements, and so you know that it is not favorable for hydrogen to exist as an atom all by itself. And again, that has to do with energy. And so this is an energy diagram, and along the top here we have different distances between 2 hydrogen atoms and potential energy here on the y-axis. And remember, a more negative value for potential energy is better. It means that the molecule is releasing energy as a result, which is favorable for the substance. And so when these 2 hydrogen atoms are far apart from one another, they have relatively high potential energy. And as they move closer to each other and eventually form the molecule H2, which we know to be the molecular form of hydrogen, it's at its lowest possible potential energy. And so this is why hydrogen prefers to exist as H2 as opposed to a hydrogen atom all by itself. It has lower potential energy. And so you will find similar diagrams when you're bonding any 2 nonmetals. Bonding the 2 together tends to lower the potential energy. And if it doesn't lower the potential energy, the bond doesn't form. And so how do we represent covalent compounds? With ionic compounds, it's pretty easy. We just write the elements, write the metals first, the nonmetals. But how do we show how the elements are arranged in covalent compounds? We use what are called Lewis structures. And in this chapter, we're only going to look at really, really simple Lewis structures between maybe 2 or 3 elements. And then in chapter 10, you'll learn how to draw more complex Lewis structures. There's a big set of rules that we'll go through. And so if you have a neutral covalent compound, so a molecule, you are going to arrange the elements in such a way that hydrogen is going to have 2 electrons around it, so that its outermost energy level is filled with electrons. Remember, energy level 1. All of the other nonmetals are going to have 8 valence electrons surrounding it. And that's a thing that's just for now. We'll go over all of the specific exceptions to those rules in chapter 10. And so in a covalent compound, you know that there are electrons that are being shared between 2 atoms, and there are also valence electrons that are not being shared, and we have terms for each of those. The shared pair of valence electrons is called a bonding pair, and an unshared pair of valence electrons is called a lone pair of electrons. And so here if we take 2 hydrogen atoms and they're bonded together, we get the H2 molecule. And so the 2 electrons, one from each of the hydrogens, is shared between the 2 hydrogens. And the atom counts a shared pair of electrons as belonging to itself. So hydrogen has 2 electrons around it, and this right hydrogen also has 2 electrons around it. So the molecule H2 has 1 bonding pair of electrons and 0 lone pairs. Another way of representing it would be to do H with a dash in between the other hydrogen instead of drawing the dots. So this is the preferred representation that we use. And we know the line to represent 2 electrons or a bonding pair. Next we have the HF molecule. If a hydrogen and a fluorine bond with one another, they're both nonmetals, so we would expect them to share electrons. And so you can see it has this one vacancy here on this side of the fluorine, and hydrogen doesn't yet have 2 electrons. So what they're going to do is get together and share a pair of electrons between hydrogen and fluorine. And so this shared pair of electrons here represents the bonding pair. But these pairs of electrons around fluorine that are not in between another atom, those represent the lone pairs of electrons. And so this over here would be the preferred representation for the HF molecule. And HF has 1 bonding pair and 3 lone pairs. Hydrogen has 2 electrons around it, satisfying its quote-unquote octet rule. Fluorine has 2, 4, 6, 8 electrons around it, satisfying its octet rule. One ALEKS example has you counting the electron pairs in a Lewis structure. And so what you're supposed to do is identify the bonding pairs and the lone pairs around whatever atom is specified in the molecule that's provided. And so in this example, they give you the Lewis structure for the bicarbonate ion. Remember, bicarbonate, that's one of your polyatomic ions, and polyatomic ions are a group of covalently bonded atoms that have an overall charge. And so here we have the structure of the bicarbonate ion. And it wants us to find the bonding pairs and lone pairs around the carbon atom. So make sure you're reading which atom it's specifying, if at all. And so here, the carbon, we look at what it's bonded to and how many electrons are around it. If a pair of electrons appears between 2 elements, that's a bonding pair. If the pair of electrons appears all by itself like it does in this oxygen, that's a lone pair. But we're only concerned with carbon. So we've got 1 bonding pair here, 1 bonding pair here, and then this represents what we call a double bond. And so there are 2 bonding pairs between this carbon and oxygen. So we have 1, 2, 3, 4 bonding pairs of electrons around carbon. And there are no lone pairs around that carbon atom. So we'd put the number 4 in for bonding pairs, 0 in for lone pairs. And so be sure that you're counting the number of pairs, not the total number of electrons. And so the concept of double bonds, that brings us to bond order. And so the number of shared electron pairs between 2 atoms, it doesn't have to be just 1 pair of electrons, it can be multiple pairs of electrons, up to 3. And we refer to that as bond order. A bond order is said to be 1 if you have a single bond. So if there's just 1 shared pair of electrons, represented here in these water molecules, that's a single bond. If there are 2 shared pair of electrons between 2 elements, like we have in carbon dioxide, that would be a double bond, and we would represent that with 2 lines. If there are 3 shared pairs of electrons between the 2 atoms, there are 3 pairs of electrons between these 2 carbon atoms, and so we would call that a triple bond. Another property about a covalent bond is bond energy, and that's the energy associated with breaking a covalent bond. Remember, when the atoms form bonds, that lowers the potential energy, meaning if you want to break those bonds, it's going to require energy. And we can talk about the strength of a bond based on its bond energy. A large value for bond energy means it requires a lot of energy, and we would classify that as a strong bond. A small bond energy, so a small value, means it doesn't take that much energy, so we would call that a weak bond. And the strength of the bond depends on how attracted these shared electrons are to the nucleus. And so in this depiction here, we have two atoms, these two spherical contours, that are bonded to one another in a covalent bond. And so there's a shared pair of electrons between the two nuclei of the atoms. And so the nuclei are repelling each other, but they are attracted to the shared pair of electrons, which is holding the molecule together. And so the distance between those nuclei and the electrons is directly related to the bond energy. The closer they are together, the stronger the attraction and the stronger the bond. The further they are from each other, the weaker the attraction and the weaker the bond. And so the distance between the two nuclei can actually be used as a proxy for bond energy. The farther the nuclei are from one another, the weaker you would expect the bond to be. The closer they are together, the stronger you would expect the bond to be. And so the bond length is the last property we'll talk about of covalent compounds, and that represents the distance between the two nuclei, as I introduced on the last slide. And you can predict the distance between the two nuclei based on the atomic size of the atom, which we talked about in Chapter 8. Remember, we looked at the trends. As you go down a group, atomic size increases, and as you go across a period, it's going to decrease. And so if you can predict the atomic size, you can also predict bond lengths. So the larger the atom is, the longer you would expect the bond to be. And so for a fluorine molecule, fluorine is the smallest of all the halogens, and so you would expect a fluorine molecule to have the shortest bond length. And as you go down the group of halogens, say to iodine you would expect to have the largest atomic size, and the distance between the two nuclei in an iodine molecule would be the greatest. And so if you relate it back to bond energy, remember, the closer they are together, the stronger the bond. So the fluorine molecule would be the strongest of these, and the iodine molecule would have the weakest bond. And so we can compare all three of those properties that we talked about. Remember, the three properties were bond order, so the number of shared pair of electrons, the bond length, the distance between the two nuclei, and the bond energy, the amount of energy is required to break the bonds. If you're looking at just bond order, a single bond will have the longest length and the lowest bond energy. And as you move up to a triple bond, assuming that we have the same two elements bonded to one another, a triple bond will have the shortest bond length and the highest bond energy, and it's going to take more energy to break all three of those bonds, which is intuitive. It may not be intuitive for the triple bond to have the shortest length, but if you put three pairs of electrons between two nuclei, those nuclei are actually going to sort of squish in and make the bond length shorter because they're so attracted to those three pairs of electrons that are between. Properties of a covalent bond. We can use the trends on the periodic table that we learned for atomic size to predict the bond lengths and bond energy. And so if you're comparing these three bonds here, carbon chlorine, carbon bromine, and carbon iodine, you can predict the size of the halogen that it's bonded to using the periodic table. Chlorine would be the smallest, iodine would be the largest. So we would expect carbon chlorine to be the shortest bond because it's the smallest atom, and we would also expect it to be the strongest bond. As we move down the carbon iodine is the largest atom of this set, and so we would expect that bond to be the longest and also the weakest. And it has to do with the attraction between the nuclei and the electrons. If it's a larger atom, the distance between those is greater, resulting in a weaker bond. If you're going across a period, remember, atomic size decreases as we go across a period. So if we're comparing carbon nitrogen to carbon oxygen to carbon fluorine bonds, fluorine would be the smallest element of this set, so that would represent the shortest bond and the strongest bond. The carbon nitrogen would represent the longest bond and also the weakest bond for the same reason. So in ALEKS, it'll give you a set of compounds to compare, or set of bonds to compare, and you need to put them in order of bond length, so shortest and longest, and bond energy. And so you have to figure out what you're comparing. In this case, we have HI, HBr, and HCl. And so the size of I, Br, and Cl you would expect to be different. And so that is going to influence the order that we put these in. And so if we look at the periodic table, we would expect iodine to be the largest and chlorine to be the smallest of these atoms. And so as a result, because iodine is the largest, we would expect the HI bond to be the longest of these three, and bromine would come next, and then HCl would be the shortest bond. And then we know how bond length relates to bond energy. The shortest bond is going to be the strongest bond, or have the highest bond energy, followed by bromine, and then HI, because it's the longest bond, would have the lowest bond energy, meaning that it's the weakest. Another variation of this example is comparing the bond order between different compounds. And so the major difference between these three examples is the bond order between the two carbon atoms. And so we have a single bond, a double bond, and a triple bond. And so with bond length, you'll just have to remember which one's the longest and which one's the shortest. Remember, single bonds are the longest, followed by double bonds, and then triple bonds are the shortest. They sort of squish in. And then the bond energy relationship is the same. The shortest bond will have the highest bond energy, followed by the double bond, and then the longest bond, the single bond here, is going to have the lowest bond energy, meaning that it is the weakest. Covalent compounds are going to vary significantly in their physical properties. So it depends on what covalent compound you're working with and what the physical properties are going to be. It's not nearly as easy to summarize as it is for ionic compounds. So some physical properties, they can be solids, liquids, or gases at room temperature. There are plenty of examples of each. Overall, their melting points and boiling points are significantly lower. And I have the melting points and boiling points listed for several covalent substances here. For the most part, covalent compounds tend to be poor or non-electrical conductors. We did come up with some examples of covalent compounds that are weak electrolytes, but when you consider covalent compounds overall, there are very few examples that are electrolytes. So in general, poor or non-conductors. And so here are several different examples. We've got gases like chlorine gas or propane gas. We've got liquid examples like acetone or hydrogen peroxide, and solid examples like waxes and fats. And there are some exceptions. There are some things called network covalent solids. If you think of something like diamond, which is entirely carbon atoms arranged together, it doesn't really fit the properties of covalent compounds. So do know that there are some network covalent solids that exist, and they don't follow the general properties that I've described here. Electronegativity is an incredibly important concept that's going to carry out in both Chem 2 as well as throughout organic chemistry. And so covalent bonding, we know, involves the sharing of electrons between two atoms. But what we haven't talked about is whether or not those atoms share those electrons equally. And in many cases, the atoms don't share equally. Some atoms are more attracted to the electrons than others. And that brings us to the property of electronegativity, which is the ability of an atom in a covalent bond to attract that shared pair of electrons. And so if an atom attracts the electron strongly, we would say that that atom has high electronegativity and a high electron density, meaning the probability of finding an electron around an atom with high electronegativity would be higher. If the electrons are shared unequally, we call this a polar covalent bond. And we have one example of a polar covalent bond between hydrogen and chlorine. Chlorine is much more electronegative than hydrogen, and so the electrons, the shared pair of electrons between hydrogen and chlorine in that bond are going to spend more time around the chlorine atom than they are the hydrogen atom. And so we call that a polar covalent bond because we have two poles. We have one partially positive end and one partially negative end. The electron density will be higher around the more electronegative atom, chlorine in this case. And we would say that a covalent bond is polar if it's between two different types of atoms. And the caveat is there has to be a difference in the electronegativity. And in this class, we're going to say that if they're two different atoms, then they're going to have different electronegativities, and the covalent bond is polar. If you have two atoms that are identical to one another, so a bond between two chlorine atoms, both chlorine atoms are going to have identical electronegativity, and so they're going to share those electrons equally. We would call this a nonpolar covalent bond because the electrons are shared equally. And so anytime you have two identical atoms, you would always say that that is a nonpolar bond because they have identical electronegativities. And there's no exceptions to that. That is true in all cases. We can assign a value for electronegativity for each of the elements. Fluorine has the highest electronegativity, and as we move away from fluorine, the electronegativity is going to decrease. In this diagram, the noble gases are not shown because we know that noble gases, based on their electron affinity, do not significantly attract electrons. Additionally, noble gases don't really participate in chemical bonding, so we aren't really concerned with their electronegativity. But for all other elements, they do participate in chemical bonding, so knowing how the atom attracts a shared pair of electrons is important. Electronegativity is related to the atomic size, and if we look at this set of atoms here, fluorine would be the smallest atom of this set, and it's also going to have the largest electronegativity, meaning it has the greatest ability to attract a shared pair of electrons. The ability to attract electrons is indirectly related to the atomic size. The smaller the atom is, the stronger the attraction between the nuclei and the shared pair of electrons is going to be. So that's why fluorine has the greatest ability to attract a shared pair of electrons. So electronegativity increases with decreasing atomic size. We have two different ways that we generally represent polar covalent compounds or polar covalent bonds. We have an arrow system, and we also have these delta systems to represent which element is more electronegative and which element is less electronegative in a covalent bond. The more electronegative atom has the electrons spending more time around it, and so we say that it has a partial negative charge, so not a full negative charge like an anion, but it has a partial negative charge. And the less electronegative element is going to be electron deficient, and so it's going to have a partial positive charge. And the two ways that we represent these partial positive and partial negative charges is we have the arrow system and the delta system. You should be familiar with both systems. With the arrow system, we have the arrow pointing towards the more electronegative element, and we cross the arrow at the partially positive end. And so if we have a hydrogen-fluorine bond, hydrogen is less electronegative than fluorine, because fluorine is the most electronegative. And so the arrow points to fluorine, indicating the fluorine is partially negative, and we cross the arrow over the hydrogen to indicate that the hydrogen is partially positive. If we want to use the delta system, this is a lowercase Greek letter delta. We would put delta plus over the less electronegative element and delta minus over the more electronegative element. You only need one representation in any case, but you should be familiar with both systems because they're both widely used. If you wanted to indicate the polarity of the OH bonds in each of these water molecules, you would first identify which element is more electronegative in each bond. Oxygen is closer to fluorine, so it's more electronegative than hydrogen. And so if we were to draw the arrows, we would point the arrow towards the oxygen atom and cross the arrow over hydrogen. If we were to use the delta system, we would put the label over each of the elements. And so over oxygen, we'd put delta negative, and over each hydrogen, we would put delta positive. So these partially positive and partially negative charges have to do with the electron density, which if you remember from chapter 7, that's the probability of finding an electron around an atom. If an atom has high electron density, that means that there is a higher probability of finding an electron around the atom. And if the atom attracts the electron more strongly, the electron density will go up. If you have nonpolar covalent compounds, such as H2 and F2, there's going to be equal sharing of electrons. And the electron density, which is represented by this space here, would be equal for each of the two atoms. And so this represents a nonpolar covalent bond. The fluorine-fluorine bond is also a nonpolar covalent bond. There's equal sharing of the electrons. Now the electron densities are going to be higher in fluorine because there are more electrons around each fluorine atom than there is hydrogen, but the electron density would be equal around each atom. Once you bond two different elements together, if they have different electronegativities, there's going to be unequal sharing of electrons. We would expect the electron density of hydrogen to be much lower than the electron density of fluorine. Because fluorine is more electronegative, it attracts those electrons more strongly. And so we have a polar bond here where fluorine is more electronegative and hydrogen is less electronegative. We use the difference in electronegativity to classify bonds as either ionic or covalent. And instead of having two separate types, it's really more of a spectrum. And we use the difference in electronegativity, we can classify something as being mostly ionic or mostly covalent. And when you have a metal and a nonmetal bonded together, the difference in electronegativity is so high, so the sharing of electrons is so unequal, that we just say that there's a complete transfer of electrons. However, with covalent compounds, they are generally sharing their electrons, and the difference in electronegativity can help us to determine whether or not it's a polar covalent bond, so there's unequal sharing, or a nonpolar covalent bond where there is equal sharing of electrons. And the difference in electronegativity, delta En, remember delta just means the difference between two values. You're subtracting the two numbers. And so what we can do is predict the bond polarity using the periodic table. For some of these, you can just use the trends of the periodic table if you know fluorine is the highest, and as you move away from fluorine, the electronegativity decreases. So in this example, we have a hydrogen-chlorine bond that's highlighted, and we need to decide whether it's polar or nonpolar. And if it's polar, there's a follow-up question, and we need to identify which atom is more negative, or more electronegative would probably be a more appropriate term here. And so if we've got a chlorine bonded to a hydrogen, which is somewhere out here if you put it in order of its electronegativity values, we would expect this to be a polar covalent bond because there are two different atoms with two different electronegativities. And the element that is closest to fluorine is the one that you would predict to be the more electronegative. In this case, chlorine is closer to fluorine, so we would expect it to have a higher electronegativity than something like hydrogen, which would be up here. And so we would write the atomic symbol Cl to indicate chlorine's more electronegative. HBr is a very similar example to the previous one. We have two different elements, they have two different electronegativities, and so we would expect this bond to be polar, and bromine still has a higher electronegativity than hydrogen does because it's closer to fluorine, and so we would say that bromine is more electronegative. In this last example, we have a chlorine-chlorine bond. We have two identical elements bonded to one another, and their electronegativities are going to be identical. And if they're identical, that means that there is an equal sharing of electrons, and that would be classified as a nonpolar bond. Another example using bond polarities, we could identify each of these substances as having polar covalent bonds or nonpolar covalent bonds, as well as identify the actual difference in electronegativity for each. In order to calculate the difference in electronegativity, you would need to be provided the values. First, let's go through and determine whether it's polar or nonpolar. If we have two oxygen atoms bonded together, they're identical electronegativities, so we would say it's nonpolar. For a water molecule, each of these bonds here, we have oxygen to hydrogen, because they're different elements and they have different electronegativities, we would say that this is a polar covalent bond. With nitrogen and oxygen bonded to one another, it doesn't matter that there's a double bond between these. The fact that they're different elements and they have different electronegativities would suggest that this is a polar covalent compound. HCl we went over in the last example, hydrogen and chlorine have different electronegativities, so it would be polar. And for the molecule I2, the two iodines are equal in electronegativity, so they would share equally, meaning it's nonpolar. All right, let's calculate the difference in electronegativity. Here you would actually need the values, so on an exam I would provide you with those if I'm actually asking you to calculate the difference. Between two oxygens, you actually don't need to know the value. The difference in electronegativity would be 0, because one number minus itself is always going to be 0. 3.5 minus 3.5, 0. For water, we're just looking at one of the OH bonds when we're looking at the difference in electronegativity. So we're just going to do an oxygen minus a hydrogen. Oxygen is 3.5, hydrogen is 2.1, so the difference between those two would be 1.4. For nitrogen and oxygen, we would do 3.5 minus 3. You're just going to subtract them in such a way that you get a positive value. With HCl, we've got 3 minus 2.1. The difference in electronegativity would be 0.9. And for iodine, we don't even need to know the number, but if we did, it's 2.5. The difference in electronegativity for the nonpolar substance would be 0. And so what we can do with these values is rate which one is the most polar and which one is the least polar. Obviously, the ones that are nonpolar are going to be the least polar, but the most polar bond is going to be the one with the largest difference in electronegativity, those OH bonds found in water. We can look at the physical properties of substances by relating the difference in electronegativity. So in this picture, we have a bunch of different compounds where each element is bonded to chlorine. So each element in period 3, sodium, magnesium, aluminum, and so on, they're all bonded to chlorine atoms. And what we're comparing is the difference in electronegativity between the elements. And so the difference in electronegativity for sodium chloride would be the highest of this set, and it has the most ionic character. It's going to be a crystalline solid at room temperature, and it's going to have a very high melting point. As we start moving across, the difference in electronegativity is going down, and for substances that we would characterize as ionic, they still have properties that are characteristic of ionic compounds. So these metals bonded to nonmetals, they are crystalline solids and they have relatively high melting points. Once we get over to silicon, which is one of our metalloids, we start seeing a mixture of properties. The electronegativity is still going down as we go across, and the covalent character is increasing, or the ability to be a liquid or a gas at room temperature with lower melting and boiling points. And one other thing to notice is that the electron density between the two elements, as we go across, as the electronegativity difference decreases, that shared area increases. So with sodium chloride, it's essentially 0. With magnesium chloride, it's a little bit higher, but there's still a general transfer of electrons. With aluminum chloride, it's even higher. And as we go up, we can see an actual shared region of electrons between these substances that we would consider to be covalent. So in general, the physical properties across a period, as we move across from left to right, the character of the substances is going to become more covalent, where the more ionic substances on the left and the more covalent substances on the right. And so here we have some diagrams where we have the difference in electronegativity versus the substances we were talking about. The higher the difference in electronegativity, the more ionic the character, and the covalent character increases as the electronegativity difference decreases. Another trend that we see is the melting point is also decreasing, and the electrical conductivity at the melting point is decreasing as well. Remember, we characterize ionic compounds as having high melting and boiling points, as well as good electrical conductivity at the melting point, so in the liquid form. And covalent substances generally have lower melting points and poor conductivity. The final topic is metallic bonding. We won't talk too terribly much about it, just a couple of slides. We introduced metallic bonding when you have only metals present. You can either have a pure metal or an alloy, which is a mixture of metals. And metallic bonding occurs when you have these positively charged metal nuclei. So the nucleus of the atom is positively charged, and it's attracted to what we call these delocalized valence electrons. Remember, metals like to get rid of their electrons to satisfy their octet rule, and so it was sort of like a game of hot potato where it was trying to get rid of its one electron so it would pass it on to the next element, but that element didn't really want it, so it would pass it on to another. These electrons here that are moving between the positively charged nuclei, these are the delocalized electrons, and they form what's called an electron sea. So all the metal atoms are essentially sharing their valence electrons. They're delocalizing them. They're moving them through this large array of nuclei. And so some properties of metallic solids. You guys have all seen metals before, so you're probably generally familiar with some of these. But the melting and boiling points of metallic solids are generally quite high. They're going to be solids at room temperature in most cases. And you can actually predict the melting point trends for metals using the groups and periods. And so as you go down a group, melting point generally is going to decrease because the atomic size is increasing and there's a weaker attraction of that atomic nuclei to the electron sea. So for larger atoms, they're further away from those delocalized electrons, so it's easier or takes less energy to melt them. Across the period, melting point is going to increase due to the increased attraction to the electron sea. Again, that's related to the atomic size. Mechanical properties of metals. They're very useful. They're very malleable, so we can put them into whatever shapes that we need. We can turn them into wires, bricks, whatever is useful. They generally are going to bend and deform instead of just outright breaking like ionic substances do. Electrical conductivity is one of the major distinguishing factors between metallic solids and ionic solids. For metallic solids, the solids are good conductors of electricity, whereas with ionic solids are poor conductors, but in their molten state, they're good conductors. So metals are good conductors in both the solid and the liquid state, which is why we use them for electrical wiring so often. And then they're also good thermal conductors. They're going to conduct heat very well. And so here are just a couple of examples of metallic solids. The first three are real ones. The last one is a fictional one from Game of Thrones. And that concludes Chapter 9.